Good afternoon, class, or good morning, whatever time it happens to be when you're watching this video. So for today, our goal is to cover chapter section 3.4a and b. Now this is a larger section. We're going to be covering some pretty important stuff as far as, we'll be talking about what are critical points, what are local maximum and minimums, what are local extremum, what does it mean for the slope to be increasing, decreasing? Where does that happen? So on and so forth. So we got some big stuff we're going to be talking about today. Now that we have a lot of the tools we're going to need for taking derivatives. So with that being said, let's go ahead and get started. So, derivatives. Today we're looking at, well, first we want to cover some vocabulary for 3.4a. So here we go. 3.4a. And, first I would like to talk about, well, let's go ahead and talk about what it means for a function to be increasing and decreasing. It's relatively self-explanatory, but we want to talk about it in terms of mathematical symbols and mathematical vocabulary. And actually, let me tilt this up just a little bit more so I can actually see the screen a little bit better. Yeah, okay. And actually, I'll back up a little too. Yeah, it's a little better. Okay, so what are we talking about? Well, let's let f, left. We want a t here. Let's let, wow, I can't spell at all. Let f be a function on the interval a to b. Now, what does that mean? I know we haven't really talked about intervals much yet in this class. In other words, I can give you an example in terms of graphically. Maybe we have some graph that it's doing something or another, and there's our graph. But in this case, I'm particularly interested in the function over this interval AB. Whenever you see this in a question, that's referring to your domain. It's saying I only care about x's that are between a and b. So it could be like a and b here, in which case I'm going to erase all of the function up to the point A and erase it up to the point B, and that's it. I'm only talking about this part of the function. It could also be that A is negative and B is negative. Wherever they are, it's just implied that A is less than B by this notation. All right, so let's keep going. We're saying we have this function over this interval A, B. Now, for this definition, we want to talk about what does it mean for a function to be increasing. So, here we go. For every x in AB, so we're making a declarative statement where this statement has to be true for all the x's between A and B here. So for every x in A and B, and in fact, we want more than just x. Let's say, sorry about that, should have had this straightened out first. For every x1 and x2, we're actually going to want two x's here. For every x1 and x2, if x1 is less than x2, if x1 is less than x2 implies, so we're saying that if the first one is less than the second one, if this implies something, if this implies that the f values, or in other words our y values, are also less than each other, so f of x1 is less than f of x2, and we're saying this is true for any x1 and x2 that we pick, then we say f of x is increasing. So what does this actually mean? Well, what it means is that for any pair of x's I pick in A and B, so long as I pick a pair where the first one is less than the second one, for any x and 2 I pick, if the f of the first one is less than the f of the second one, and that's true for any pair I pick, then the function must be increasing. Now, and we can think about it a little bit. Suppose we have this line, y equals x. Then in this case, the function is increasing everywhere. Why? Well, for any x's I pick, if I pick an x over here and an x over here, so long as my first x I pick is less than the second one, then my second f of x is always going to be bigger than the first f of x, and you can clearly see that on this line here. So this is an example of a function is increasing everywhere, and it also holds this definition such that if you pick any pair of x's, so long as the first one is less than the second one, then their f values must also be less than the other one. Okay, so that's f of x is increasing. Now for decreasing, we're going to have pretty much the exact same statement if x1 is less than x2. So again, we're making the statement that, yes, we're saying for every x1 and x2, but specifically, you're only allowed to pick x1s and x2s such that the first one is less than the second one. So if we pick any two x's and the first is less than the second, if that implies that f of x1 is actually the bigger one, then f of x is decreasing. And if we use the exact same example, but suppose instead we have y equals negative x, then again, here you can see that for any two x's I pick, so long as the first one is less than the second x, then the f of x values, the f of x value of the first one is going to be larger than the second because this is always going downward. It's always decreasing. And so this example follows this definition and implies that this function is decreasing everywhere, which you probably already knew that just by looking at the graph. Okay, great. So nothing too fancy here. We've just covered basic definitions for what does it mean to be increasing and decreasing. But now we'd like to take those definitions and apply them to what does that imply the derivative is doing. So we're going to write some alternative statements that are equivalent. So they're the same statements, they say the same thing, but with regard to the derivative. So the next thing we like to say is that, and this you're going to want to hold on to, we're going to need this later in this chapter, positive slopes imply f of x is increasing. Why is that true? Well, again, think about our example where f of x equals x. This is where y equals x. What's the first derivative of this? Well, the first derivative is just a constant 1. So that means for any x value, the slope is always 1. Well, what is 1? Is it positive or negative? 1 is positive. So this tells us the slope is positive everywhere. And if you think about climbing a hill, if the hill is sloping upwards everywhere, then in order to climb that hill, your elevation is going to be increasing from every point you climb your hill. So this allows us to more directly be able to tell where is f increasing based off of what the slope is doing. Or in other words, what the first derivative is doing. So by the same exact argument, we also have negative slopes imply f of x is decreasing. So the nice thing about these definitions is that you no longer have to pick some arbitrary x1 and x2, make sure they're less than each other, and then test their f values. There's a lot of step-by-step in these definitions in order to say something is increasing or decreasing. Whereas here with the derivatives, all we have to do is check the sign of the number. Is it positive or negative? It's much easier, much cleaner, and these definitions, they're equivalent. They imply each other. So this is good to hold on to. Yeah, I think that's everything I wanted to say there. Yeah, so we had this idea of positive slopes imply increasing and negative slopes imply decreasing. But now we'd like to talk about what's going on over an entire interval. It's all fine and good to say that a function is increasing at a particular point, but what if we want to more generally say that the function is increasing for all of these x values that are between 1 and 2, or all of these x values between 2 and 3, or whatever? Then we can more specifically say for what values of x this is happening, rather than just trying to find each individual x one at a time. So this is going to be useful to us. So what do I mean by that? Well, again, this is more or less just an extension of the definition we already have here. So, suppose f of x, is differentiable on the open interval a to b. So we're just starting with the assumption that we can take the derivative, because if we can't take the derivative, then this stuff doesn't even matter. Like, we can't tell anything based on these definitions. So assuming we can take the definition, or the derivative, sorry, if f prime of x is greater than 0, in other words, it's positive, for all x in AB. So for any x you pick in an interval, if it's greater than 0, if it's positive, then f of x is increasing on the interval, on AB. So it's increasing over this entire interval. Okay, this is nice. Now we can pick out intervals, and if we can show that for any x in there it's greater than 0, then great. We now can say that the entire interval is increasing, and for any x in there, this is happening. That way, you don't have to pick individual x's and test them, because we'll already know, well, if they fall in such and such an interval, then they must be 0. Or, I'm sorry, then they must be increasing. Alright, great. And then, by the same kind of idea, if we flip it, if f prime of x is less than 0 for all x in AB, then f of x is decreasing on AB. And there you have it. This is going to give us our initial definitions that we're going to work with and build off of for 3.4a. As we move forward into 3.4b, you'll see that we start to expand more on this and start to apply it in other ways. But for now, this is all we're doing in Part A. So what can we do this? What kind of word problems, examples, questions could you expect to get based off of this stuff? Well, mostly the kind of questions you're going to get is, given a particular function, where is it increasing? Where is it decreasing? Where is it doing neither? Well, what does that mean? Where is the derivative not increasing or decreasing? Well, we've already discussed that if it's positive, that's increasing, and if it's negative, it's decreasing. The only way a derivative could be neither is, well, one of two ways. One, it could be undefined, or two, the slope could be zero. In the case where a slope is zero, then it can't be increasing or decreasing. What do I mean by that? Well, let's look at some examples first. So this first example, suppose f of x equals x squared. Then in this case, f prime of x is equal to 2x. So here we have the derivative, and we would like to know, where is this increasing? Where is it decreasing? Well, first, let's talk about, where is it neither? So if we set this equal to 0, you divide by 2, then x equals 0. So at x equals 0, the slope is doing neither. Well, what does that mean? Well, that tells us it's a point where the slope could be changing. How do I know that? Well, think about it. If f prime of x is this line, 2x, well, what is 2x? We can actually graph that and take a look at it. The line 2x is just a regular old line with a slope of 2. Y equals 2x. This is the graph of the first derivative. So what do we see here? Well, at 0, we have the point 0, 0. Well, what else is going on? Well, this tells us that the slope for our original function, x squared, is 0. Well, does that make sense? Well, yeah. I mean, x squared, if we graph it, it's just your basic old parabola. And what's happening at x equals 0? Well, at x equals 0, if we try to imagine the tangent line at that point, it's just a flat horizontal line because it's decreasing, decreasing, decreasing. It flattens out, and then increasing, increasing, increasing again. So the slope there is 0, which is exactly what this line tells us. So this is very useful when you're trying to interpret things about other functions. So what else does this tell us? Well, this also tells us, if we draw a number line for the first derivative, oops, hold on, let me pause this for a second. Alright, and I'm back. So, yeah, I guess there wasn't much of a pause for you guys, but we had some things going on here. At any rate, what are we looking at here? So, right, we're making a number line for the first derivative. So, why am I doing this? Well, this is what's going to allow me to talk about what are the intervals for which this function is increasing or decreasing. Why is that? Well, if I label these points where the slope is 0, where I have this change happening, then I now know that this is the only point where it's not increasing or decreasing. Everywhere else, it has to be doing one or the other, which we can clearly see from this graph. On one side here, it's positive, but on the other, it's negative. Well, if I didn't have the graph drawn, how else would I be able to tell? Well, another way to tell is just pick numbers that are on the right side, plug them into your first derivative, and see what you get. So if I check here, f prime of 1, since 1 is to the left of 0, then f prime of 1, I'm going to get 2. That's positive, therefore, I must be increasing on this side, which is true because the function is positive on this side. So what else does that tell me? Well, it tells me that I am increasing on what interval? Well, not at 0 because it's 0 there. So not including 0, it's increasing for any x bigger than 0. So what is that? That's increasing from 0 to infinity. All right, great. What's happening on the other side? Well, let's plug in -1 to our first derivative. So what's f prime of -1? Well, 2 times -1, that's -2. It's negative, and so what's happening? We are then decreasing on what interval? Well, for any numbers that are less than 0, going in this direction forever, so towards negative infinity. And then what's the upper bound? How far up can I go? Well, so long as I pick a number that's less than 0, because at 0 it's 0, then I'm good. So I'm decreasing on the open interval from negative infinity to 0, and I'm increasing on the open interval from 0 to infinity. So there you have it. That would be the final answer for this question. And this question also serves as a good example where the slope, there could be a point where it's neither increasing or decreasing. That's an important point to take home, that there are some places on a graph such as x squared or other functions where maybe it's not increasing or decreasing, and that's perfectly okay. That's a valid answer. So keep that in mind as you work through these problems. Use those points to indicate where it might be crossing the x-axis, where the first derivative might be changing sign. Test both sides of that point, and then you'll be golden. So there you have it. That's 3.4a in a nutshell. Let's see, we're at 22 minutes right now. There was one other example I wanted to cover, but let's go ahead and hit 3.4b. I want to make sure I go over all of that before the end of the video. And then if we have time, I might go back to another example from this section. So we'll put a pin in it. If we don't have time to go over, of course, feel free to ask me during Q&A today, and we'll talk about what that question was. Otherwise, hopefully we'll get to it, and then we'll talk about it at the end of the video. So let's go ahead and change gears and take a look at 3.4a part B. 3.4b. So what's going on here? We've talked about derivatives. We've talked about what does it mean to be increasing and decreasing. We've talked about that the positive or negative sign on a slope tells you if it's increasing or decreasing. But what else? Well, now we're ready to talk about something called local extrema. Local extrema. What is local extrema? Well, for that, let me make sure I write this definition down correctly. So this is where a function changes from increasing to decreasing, or vice versa. You could be decreasing to increasing, so it's not stuck in that, or vice versa. This is the definition for local extrema. Furthermore, it's kind of a follow-up. If there exists an interval. What is an interval? Well, that's like what we had before with our AB business. So if there's an interval AB such that for all x in the interval, so in AB, there exists another variable, another value, another c. There exists a c in AB. I'll move so you can see it a little bit better. There exists a c in AB such that f of x, now remember this was for all x in this interval. For all x in this interval, there exists somebody in here such that f of x is less than or equal to the f value for that c. So in other words, everything in this interval is less than or equal to this f of c value. Then, as you might guess, f of c is called a local maximum. More specifically, a local maximum is also a type of local extrema. So these two things relate to each other here. And if you flip the statement, if you keep the same thing, so I'm not going to rewrite the whole thing, but if you have the same thing, but instead f of x is greater than or equal to f of c, so for everybody in the interval, it's then greater than or equal to this value in the interval, then we call f of c a local minimum. And this is a type of local extrema. So what does this tell us? Well, it tells us two things. One, this means that local extrema, where we have a change between increasing and decreasing, this also gives rise to local maxes and local minimums. And whenever you have a local max or a local min for your function, then that means it should be changing signs on either side of it for your slope. This should be switching to increasing or decreasing, or vice versa. Or in other words, what does that tell us? Well, actually I don't want to quite get there. We'll get there. More specifically, it tells us that these candidates for points that could be local maximum minimum are going to be places where the slope is 0, because that's where, as we saw in our previous examples, that's where the slope is changing signs, or is possibly changing signs, from negative to positive or positive to negative. So it becomes very important to find these places where the slope is 0, or, as we'll find out, where the slope is possibly undefined. We'll have an example of that in a few minutes. Right. So what do we have here? All right, just a simple first example to explain this. So consider the function 3x squared. Oh no, I'm sorry. Not 3x squared. X cubed plus 3x squared. Yeah, that's what we want. Now, as we've found out from looking at where is it increasing and decreasing, in order to do that, we need to talk about the derivative. So let's go ahead and find our derivative. And here we're just using our power rule. So this is 3x squared plus 6x. Okay, so far so good. Now what? Well, we want to find the points where this function, the first derivative, we want to find out where this graph crosses the x-axis. Why? Well, where it crosses the x-axis, that's a potential point where it might be changing signs to the left and right of it. If it crosses the x-axis and it's positive than negative, then that is a candidate for a local extrema. So we want that. We want to know where this equals 0. So I'm going to set it equal to 0. And it looks like I can factor out a 3x. So I'm going to have 3x times, on the inside I'll have x plus 2. And now I can see better that one of my critical values for where this equals 0 is x equals 0, or if x equals negative 2. So in this case, I have two places where the slope is 0, two possible candidates for local extrema. Now I don't know their local extrema yet until I test them for increasing and decreasing. It has to happen, the sign has to flip on both sides of it. That's what this definition says here. So let's go ahead and check that. So here's my number line for f prime of x, and I've got negative 2 and 0. At these points, the slope is 0. Okay, well now what? Now, just as before, I can just pick whatever x I like in these intervals and test them. Because these are the only places where it hits the x-axis, I know for these intervals, they have to be all on one side or the other of the x-axis. But we have to test it to find out. So for the far right, I'll just plug in 1. That's an easy number. So f prime of 1 is equal to 1 squared is 1 times 3 plus 1 times 6 is just 6. 3 plus 6 is 9. 9 is positive, and so I'm increasing here. Now I need something to test in the middle, so I'll just use negative 1. So f prime of negative 1, that equals, okay, negative 1 squared is 1. 1 times 3, that's just 3. And then negative 1 times 6 is a negative 6. So I'm going to get negative 3. This is a negative number, so I am decreasing in the middle here. And then lastly, I need to pick something over here. Negative 3 will work. So f prime of negative 3. Now, and be careful to make sure that you're plugging these numbers into the first derivative here and not your function x, because they're going to give you different values and you don't want to do that. So we plug in negative 3. Negative 3 squared is 9. 9 times 3 is a positive 27. But then I want to subtract 6 times negative 3, so that's a negative 18. 27 minus 18, that's a positive 9. And so I'm positive on this side. So I actually get a bunch of information from this. One, I know that the function, my original f of x up here, is increasing on negative infinity up until negative 2. Union, so union, this U sign is just a fancy symbol for and. It means I'm including this interval and some other interval. So the other interval I'm including is this interval from 0 up until positive infinity. And then I also know that it is decreasing on this middle part, negative 2 to 0. But it gets even better than that. What else do I know from this? Well, based on this definition for local extrema, I know local extrema occur where the sign flips, it changes. I'm looking for where it changes from increasing to decreasing. So it changes here at 0, but it also changes here at negative 2. So which one is which? Well, a local maximum occurs where the value is bigger than everything. So if I think about f of negative 2 here, what this is telling me about the first derivative, it means as I approach negative 2, my slope is positive. So I'm increasing as I come towards negative 2. I flatten out for 0. And then after that, here in the middle, I start decreasing, I'm decreasing again. But what was that picture I just drew with my hand? Something like that. So anytime you have positive on the left side of a number and then negative on the right side, that is a local max. So this is great. Now I know I have a local max, at x equals -2. But by the same argument, if I look at 0, that means I'm decreasing as I'm approaching 0. When I hit 0, I flatten out, and then I'm increasing again. So it has a U shape around 0. But what is that? Well, that means this point at 0 is smaller than all the other points to the left and right of it. So it's a local min. So there's a local min at x equals 0. Let's see, can you guys see that? Is that on the screen there? Yeah, it is. Okay, we're good. So there we go. So just from taking the first derivative and then drawing this number line for our first derivative, labeling the points where it's 0 and then testing in the middle, we got all of this information down here. We know where it's increasing and decreasing, and we know where local maximums and minimums occur. So this is great. What else can we do with this? Right, so now we want to start talking about these specific cases where it's 0 or it doesn't exist, when the derivative is 0 or it doesn't exist. So let's see, I'm going to have to erase all of this for a moment. And let's see, we're at 36 minutes now, so may try to pick up the pace just a little bit, make sure we hit everything we want. And of course, if I end up going over something too fast, by all means, let me know. We can talk about it. Last thing I want is to lose anybody. But I think we're going slow enough, and we're talking about the examples, so we're able to explain the vocabulary and what's going on here. So, what's this other definition I want to talk about? Well, what we have now is, and this we've kind of already touched on, but I just want to write it out in words. So, for C in AB, in an interval AB, if f of c, so we're talking about the y value at c, if f of c is a local extrema, oops, I cannot spell, extrema, which means that it's a local min or max. If it's a local extrema, then, and this we've kind of already touched on, f prime of c equals 0 or does not exist. Now, this does not exist case we'll actually talk about in a second, but just in our last example, you already saw when the slope is 0. And all this is saying is that basically any of your extrema, your local mins and maxes, they're always going to occur at points where one of the two happens. And that's because it's only at these points where it's possible the first derivative function could touch the x-axis. And it's because that when you touch the x-axis, that's the only place where your function, that's the only time it could cross the x-axis. And when it crosses the x-axis, then you can have positive numbers and negative numbers to the left or right side of the c value. So this is a very important concept. It's a very important test. This is actually called the first derivative test, where you take the first derivative and then you set it equal to 0, solve for those x's. These become test candidates. All right, so we've already seen an example where the slope is 0, but when does the slope not exist? That seems like a weird kind of case. Well, think about the example where f of x is equal to the absolute value function. Now, you've probably seen this before. Basically, on the graph, it just looks like a V thing, a V graph, where it it comes at 0 and it meets, and we have this sharp corner. And actually, I believe there was a previous video where we talked about sharp corners. This is what we mean by sharp corners, and more specifically, this is a place where the slope doesn't exist. Why is that? Well, let's think about what is the derivative. Well, a piecewise function we can also rewrite as a piecewise function, where for these positive numbers, it's just the y equals x line, right? So if x is greater than 0, it's just x. But if I plug in a negative number, if x is less than 0, then I want to flip the sign on it so it stays above the x-axis. So this is negative x. But if I take the derivative, then what do I have? Well, then I have 1 and negative 1 for x positive and negative 1 for x negative. Well, what does that mean? That means if I'm trying to find out what the derivative at this point 0 is, then I have to look at, okay, well, from the left side for negative x values, the slope is negative 1 always. So from the left side, as I'm approaching 0, it's saying slope's negative 1, negative 1, negative 1, negative 1. As I get closer and closer to 0, from the left side, the function thinks the slope is negative 1. So the limit, as x approaches 0 from the left, of my derivative, f prime, is negative 1. But from the right side, as x approaches 0 from the right on my first derivative, it's equal to positive 1. These clearly don't equal to each other, and so the limit does not exist, and so the derivative doesn't actually exist at that point. But what happens? We look at the graph here and we can see, well, obviously, the point 0, 0 on an absolute value function, that's a minimum. It's smaller than any other values to the left and right of it. So it's a local minimum. So what does that tell us? That tells us anytime you're trying to test for local extrema, anytime you're trying to test using the first derivative test to find where we have the local maxes and local minimums, not only when you draw your number line do you have to label points where the slope is 0, you also have to label points where the derivative does not exist. So this is very important that you check both cases and then label points in between them, so on and so forth. Okay, so this is pretty good. We've pretty much covered the basics for the first derivative test. Let's see. Don't want to keep you guys too long. Yeah, so just to clarify some definitions a little bit. So we've already specified these local extrema, they have to be at points where the slope is either 0 or does not exist. Well, these potential local extrema, we actually have a name for them. They are called critical points. Or sometimes they're also called critical values. So critical values or points. This is a vocabulary term you're going to want to remember. You may have some Hawks Learning questions. They're going to ask you, find the critical points for f of x. Well, then you got to know what a critical point is. So a critical point is, so the first key word is assuming f of x is continuous. That's important here. Assuming f of x is continuous at C, where C is a potential candidate for extrema, it's a critical point, C for critical point. Assuming f of x is continuous at C, then if f prime, we're looking at the first derivative, of C is 0 or does not exist, then it is a critical point. So there's two things that we want to highlight here. One, critical points are where the slope is 0 or doesn't exist. But two, and this is an important thing that students often forget about, in order to be a critical point, the function must be continuous at that point. Before you even test the first derivative, it has to be continuous at that point to be a critical point. Well, why does that matter? Do we have any examples where that actually comes up? Yeah, look at this example here. Suppose, let's see, and I'll erase the right side here. So suppose that f of x is equal to x squared minus 1 divided by x. Now, sure, that numerator I could factor into its conjugates, x plus 1 times x minus 1. But even in that case, after factoring it, I can't simplify that any. This is as simple as this fraction gets. So where do I have points of concern? Well, the function is not continuous at x equals 0. When x equals 0, I have a problem. For one, the limit doesn't even exist. Why is that? Well, without getting too much into the details, if you actually graph this function, and you can put this function into Desmos or on your calculator or whatever, just see what it looks like, it ends up looking, and let me make sure I do this correctly, something like this, where at 0, from the left and right side, they both zoom off to infinity in opposite directions. So the limit doesn't exist. It is discontinuous at this point. And because it's discontinuous, it's not even a possible critical point. So for this particular question, we actually say that there are no critical points. Because if we think about it, even if you try to figure out what the value of x equals 0 is, if you try to find out what f of 0 is, you can see that both on the left and right, there's values that are infinitely bigger and infinitely smaller. So there's no way it could be a local max or a local min. So we don't even consider it to be a critical point. Well, why else are there no other critical points? Well, remember, critical points come from the first derivative. So if I take the first derivative here, I'm going to get, so I got to use quotient rule, derivative of the top, 2x times the bottom minus the top times the derivative of the bottom, that's just 1, divided by the bottom squared. And I can simplify this a little bit. I'm going to have 2x squared minus x squared plus 1 divided by x squared, which is just x squared plus 1 divided by x squared. And I could divide into both parts across this plus sign. So that's going to be 1 plus 1 over x squared. But now the question is, where does this equal 0? There's no x value I can plug in that's going to make that 0. But there is a point that's undefined. If I plug in x equals 0, well, that's bad. I can't do that. What's 1 divided by 0? So the slope does not exist at x equals 0, but even though it does not exist, we don't call it a critical point because it is discontinuous. And because it's discontinuous and because it's the only place where we have the derivative do this, we then say there are no critical points. That also means that there are no local maximums and no local minimums. So there you go. That's a good example where it's important to remember the entirety of this definition for the critical point. So that's about all the time we have. Of course, there's some other examples we could go over, but at this point, I've showed you everything that you need to be able to do these questions. At the end of the day, this all boils down to, 1, is your function continuous everywhere? If it is, then great. Don't even worry about checking to see if you have potential discontinuities then. So make sure it's continuous at your points that you're checking. Once you've done that, then you can look at your first derivative. What do you do with it? You set it equal to 0, but you also want to consider where is the first derivative undefined. Label those potential candidates on your number line. So that could be C1, C2, C3. This is where it's 0, or maybe it doesn't exist. This is for your first derivative. Test your points in between. That's going to tell you where your function is increasing and decreasing. And then anytime you see the sign flip on either side of it, that means it's a possible local max or a local min. So other things to keep in mind, there are some examples, and we don't have time for it, where you might have the same sign on both sides of a critical point. In that case, it is not a local max or a local min. So don't label it as one. That's going to be incorrect. A local max or min only occurs where the sign changes on either side of it. So keep that in mind. Yeah. So that covers everything that we wanted to talk about today. I apologize for running a little long, but I'll try to make some of the future videos a little shorter for you guys. So, all right. That's all I've got for you guys. Of course, let me know if you have any questions, concerns. Email me. We can talk about it. And of course, we can also talk about it today during our Q&A. So, yeah. That's everything I've got. So, best of luck.